Okay. Okay, so let's just recap what we were talking about. We're talking about various types of forces, and we already encountered, I think, the gravitational force, and we're looking at things like the normal force. This is the force due to compression of an object, and it acts in the perpendicular direction. Wow, so many technical problems today. Okay. Just reopen it. Wow. Weird. What's happened? Okay, that's back. That's coming on. It's very mysterious. I don't know what's going on here today. Also, we have friction. We'll do more of friction in the next chapter, but for now, basically, it's simply we can understand it as a force that depends on the movement of the object and it acts in the opposite direction to where you attempting the movement. So in this case, if you're sliding the block forwards, then it'll act backwards. And tension, this is basically force due to a rope or a string, and you'll get questions with things like pulleys in them, but basically for purposes what we'll do, they're entirely just mechanisms to change the direction of the force. So really it doesn't do anything, but it's actually not really so different, or in this case it's absolutely completely the same between these two diagrams as you pulling on the rope horizontally like this, or you pulling down on the rope like this. It's in terms of the forces, they're identical. So well, this third one would be a little bit different because there would be gravitational force down on the block, which for these ones there's gravitational force, but it is cancelled out by the normal force. Okay, and so we did Newton's third law, so famous, forces act in equal and opposite directions. Maybe one of the main points to remember here is that it's always forces that act on two different objects, so it's one force acting on another object. So there's always two bodies involved, and they are equal and opposite. So gravitational force or normal force are some examples. We did this example, and we did this particular sample problem. Have a couple more sample problems. Would you like me to go through more sample problems? Or? No? Well, okay, so maybe just quickly, just strategies for solving these types of problems. So in this particular example, you have an object which is pulled up by some rope, and it's on an incline. Right? So whenever you have something that's on an incline, it's kind of a typical example of a two-dimensional type of problem. So that in this case, you would draw, well, no pens either. So on an incline, you have some, got that badly, and so you have the tension of the rope that's up. This is at an angle theta, and you'll have gravitational force down, but you'll also have a normal force, which is pointing perpendicularly to the plane. So basically, you can split this into two different directions. So it's maybe convenient to choose the directions which are parallel and perpendicular to the plane. So we can look at the components of this gravitational force, and well, you can convince yourself that that angle is actually the same as the angle of the incline. This will be mg cos theta. This will be mg sine theta. And so basically the total force in the kind of the perpendicular direction would be the normal force minus mg cos theta. The force in the parallel direction would be, well, it's called T minus mg sine theta. So I haven't really even read the question yet, but I mean, this is such a common kind of setup so that you can almost just immediately draw this kind of situation for the forces. And then finally read the question. So what is the box's acceleration along the inclined plane? So usually in these ones the thing slides along the inclined plane, so that means that the total force of this thing is zero. And then so in this case we're given this one. So this one is 25 newtons, and we're given that the mass is 5. So in this case, I think we just use the second equation. So we know basically all these parameters, right? So we know that one, we know the mass, we know the angle, and so you just have to apply F equals ma to this, and then you can get the acceleration. So it's done like this one. And another sort of classic question is when you've got two blocks on a plane, and there's a force applied to one of the blocks, and then it's pushing the other block, right? So this is another kind of classic type of example because it involves more than one body, and so what that means is that you can apply Newton's laws in, well, in this case, like 3 different ways. So you can apply Newton's laws to block A alone, or block B alone, or maybe a combined system together. So, right, so in this case, the first question is to ask what is the acceleration of the blocks. So you got the force applied, which is known, so that we know that it's the applied force. You also know the masses of each of the blocks, right? So this one is 20 newtons. This one is 4 kilograms. Got another block here, 6 kilograms. And so to look at the other forces involved, you need to think of the forces at the interface of this. So just from Newton's third law, you'd have a force on block A due to block B, and then another equal and opposite force on block B due to block A. In fact, this is the force that actually will push the object, right? So, object B, rather. So, the problem is that we don't really know what these are. And the way that you can kind of view this is in terms of applying Newton's laws to, as I said, either A or B or them together. So if you look at sort of A only, then you'd write an equation that's sort of like, so force applied minus force AB would be equal to MA times A. For B only, it'd be force BA with MBA. And A plus B, it would be the total force of all these three things together. And so it'll be force applied minus force AB, well, plus force BA. I've taken it so that these are all positive. So, yeah, so sorry to confuse you maybe with the notation that we had before, but I've already implied the directions in this diagram and what I mean by that. So actually in this case, the magnitude of force BA and force AB are the same, so actually these cancel, and the total mass of this thing is MA plus MB equals to A. So it's basically, those are all the equations that you can write down. We can't really solve A with this equation because we don't know what that is. We can't solve this one either because we also don't know what that is at this stage. This one, these actually cancel, so we're actually just left with one variable and one unknown. One equation and one unknown variable. So this one we can solve, and so from this one we can get A. And then once you know A, then you can actually work out the other things. So what is the horizontal force FBA on block B? So this would be the natural one to use. We've worked out A from part A, stick it into there, and then we'll get that force. So the key thing is that you can apply Newton's laws in different ways. Okay, so any questions? No? Alright, so let's move on. Let's move on to the next chapter. So this is another sort of force chapter. But I think we're going to talk about different types of forces, and namely we're going to talk about three types of forces: friction force, drag force, and centrifugal force. So alright, yeah, so let's just talk about each one of those. Friction one is maybe the one we cover in most detail. So so imagine you're pushing a large crate here, and it's dragging on the floor, so it's kind of hard work to push it, right? So you can kind of deduce certain things about what the friction force is just by more or less common experience, right? So we can think of various situations of friction acting on this box. So for example, maybe this box, maybe what Bob does is to give this box a big push at the beginning, and then so just to do some kind of thing, not the best demo, but all right. So you slide it, and give it a big push at the beginning, and then it eventually comes to the cell. Right? So if you plotted the velocity of the object, it would have some large velocity at the beginning, it would gradually sort of slow down and come to a stop at some point. Right? So you can think of that kind of situation. Or you can think of the situation where Bob is sliding the crate across the floor at a constant velocity. So he's constantly pushing it, otherwise obviously it'll stop. And then in order to maintain constant velocity, it's always providing a force. And so in terms of the velocity profile, it's kind of like constantly. Another situation is that the crater is so heavy that you cannot actually move it. Right? So it's pushing on it. So it's, well, maybe it's not the best example, but so if I'm pushing on the TV here, I'm pushing it with some force, but it's not moving. So I'm definitely providing a force, but nothing's happening. So those are sort of three situations where, of course, friction is involved. And we can deduce certain things about the nature of friction just from this kind of observation. So, these are pretty common sense observations, as you would know from daily experience, right? So, right, so, okay, so maybe I've explained everything already here. Yeah, so the kind of questions that we might think about is, so how does the friction force change if ball pushes in the opposite direction? So I think most of you would appreciate that same kind of thing. It's just that the situation is reversed. But so if he was pushing in the opposite direction, what you would also notice is that, so say we're looking at, let's say the third scenario here where he's pushing on it and it's not moving. So had he been pushing with this force, so this is ball, this is the guy, then the force is acting this way, but obviously friction would be acting in the opposite direction. So it's the whole thing's flipped. Yeah, and you can also think about, for example, for the third situation, well, he's pushing with some amount of force, but if he's not pushing with the same amount of force, would anything be different? So, okay, so let's try and deduce a couple of things from these scenarios. So let's start with the third case. This is the one where I'm pushing on the TV, but nothing's happening. Right? So, so I'm pushing on something and it's not happening. Nothing's moving. So, what can you say about the relationship between big F and little f? More or less on the slide. Either it's too easy, nobody wants to answer because it's so easy that they don't want to answer, or it's hard. Yeah, zero. Right, so you mean the sum of them is zero, right? Yeah. Yes. So, yeah, it has to be because you're pushing on it, nothing's happening. The velocity is actually just zero, right? It's what we observe. Velocity is zero. The velocity is zero, then acceleration is zero, right? And if the acceleration is zero, the force must be zero, right? So basically, from the fact that v equals zero, like for all time, we can figure out that A is zero, and then from A zero you can work out that the total force is zero, and then because the total force is F minus little f, so this force and that force, so So little f must be the same as big F, right? Fine, but okay. So, but what if I pushed with? So say I did this, and initially I was pushing with 10 newtons. So basically, what we've just deduced is that if I'm pushing this with 10 newtons this way, frictional force must be providing a force in the opposite direction with 10, right? Okay, but what if I now relax a bit and I push with 5? What would the frictional force be? Yeah, also 5. Okay. So what if I push with 1? 1, right? So this thing is a kind of a it's a dynamical thing, right? It's as if it knows what force you're pushing with, right? So it's just, whatever I apply, obviously it doesn't know what I'm going to apply first, right? It doesn't know if I'm going to do 10 or 5 or 1 or any number. But, somehow the whole dynamics is that it provides a force that exactly matches whatever that you're applying. Now, if you think of it like that, it seems kind of magical, but it's basically because, essentially this is a kind of a mechanical system, and the mechanics, the atoms in the system kind of deform in such a way such as to exactly provide a force to compensate whatever the applied force is. Right? But anyway, at the end of the day, it's this kind of, you might say it's sort of a dynamical kind of system, because dynamical in the sense that it's not just like a constant force that is providing, it actually just it matches whatever you're doing. So but of course, if you provide it with a large enough force, then it will start moving, right? So if when you're trying to move something, obviously what you do is you don't just like come in like brute force and just push with the largest force you can immediately, right? Because then it'll just go flying across the room. So of course the kind of thing that you do when you try and push something is, you just say, you do something like, okay, I'm going to push on it, oh, it's not moving, all right, I'll push on it a bit harder, oh, it's still not moving, okay, I'm going to keep on increasing the force until it starts moving, and then you go, okay, it started moving now, and then you ease back on it, right? And then because, if you keep on doing that, it'll just get faster and faster, and then you're running across the room chasing the TV, right? So basically what you do is you keep on increasing until you overcome that static friction, and so there's some kind of limit that the static friction can actually provide, right? So you're pushing on it, and to work that out is a kind of a pretty hard thing. Like if you just gave me this TV and then you said just find what the static friction is, right? It'd be very hard to calculate. I mean, you'd have to look at all the wheels and the weight of the whole thing. So it's just about impossible to actually calculate what that is. So this is a completely sort of phenomenological thing. You kind of have to just do an experiment. You get a force meter, keep on pulling it, and then you go, okay, fine, it's something. It's like I need 50 newtons to move this thing. It's just like you have to more or less do a measurement, but there is a kind of there is a formula, if you like. So the formula to find what this force is that you need to push it is given by something like this. So this is the normal force that is acting on the object. So in this case, you've got some crate which has got mass m. Gravity is down, so we know that the normal force is going to be in the upward direction. And there's this kind of phenomenological kind of constant that you put in there. And this is a number that's just between 0 and 1. And this is the thing that you just basically have to just go and measure. And so the product of this coefficient and the normal force is basically this upward. Now, what this formula is kind of telling you is that the heavier the thing is, the harder it is to move. And so that makes complete sense, because if this TV, I don't know how heavy it is, maybe it could be like 20 kilos or something. So if you measured the force to move the TV, then you'd find it to be some number. And then say you stack some weights on this thing here, right? So you added another 5 kilos, 10 kilos, so forth. Then what you'd find is that the force that you need to move it would start to kind of go up as you stack more and more weights on it. And so that is kind of fairly, well, it's kind of, it kind of makes sense from the point of view that things which are heavier are harder to move. But basically, originates from the fact that the heavier the thing is, the more it's pressing into the ground, and the more, if you look at this thing microscopically, then there's, all these little, these edges are quite rough, and all these rough edges are more and more pressed into each other, interlocking, and it's just harder and harder to kind of basically break those kind of connections between the object and the ground, right? So so it's basically, it has this kind of relation. This mu, you basically just have to be given that. So often in problem-solving questions, you're just given the coefficient, and then you simply multiply that by the normal force. Okay. All right. Now, kinetic friction is a little bit different, because in this case, the force is not really dynamic in the sense that static friction was. So, what do I mean by that? So, for example, let's go back to that first case when, the second case actually. Second case, when you're just providing a force and it is moving at constant velocity. So this would be like, the sensible way to push something across the room, right? So if you're trying to move something from A to B, then you are pushing it at constant velocity, and then you kind of walk at a constant speed, right? So in this case, what you do is you're just always providing a constant force. And so the fact that it's constant velocity, so what does that mean about acceleration? So if you got velocity times time versus time graph, and it's like constant like this, so how do we get the acceleration from such a graph? I get the feeling some of you know this, but you're just not speaking up. So, you know, so in this case, I said V0 and A0 and so forth, right? So in this case, V's said a half, right? Yeah. So derivative of a half. 0, yes. So acceleration is 0, yes. So actually everything is the same as before. So force total is 0. Force total is 0. And so in other words, the force is equal to the friction that we're providing. That's fine, you know, that's all fine, except that I've done it, I've basically written down exactly the same equation and did exactly the same deduction here. So I've gone F is again, so this one was equal to static friction. This one is equal to, so I'm going to distinguish this case of kinetic friction. So of course F must be equal to Fk. Now that almost looks like Fk is equal to Fs, right? Is that true? Yeah.
Why is the equation F total minus 0?
Because Newton's law. So F equals ma. We established that A is 0. So F equals ma, A is 0, then F is 0. Yeah. So F total is, and in this case again, providing force, friction. In the first case, it was the case where, you know, I'm pushing it, nothing's happening. Second case, it's the case where I'm going to pull it this time. It's going to move at constant velocity towards me. So it looks like Fk is Fs. Is that true? Okay, so let me just give you an answer, I guess. So it's actually not generally true. Fk is not equal to Fs, even though, you know, well, what I've written on the board kind of makes it look like it is. Because basically, I never said what really this big F was here, right? So this big F could be actually something different in this case. So maybe it's better to even write this as F dash in this case. Now, you have to think to your kind of your experience in order to kind of work out whether Fs is, you know, bigger or smaller than Fk or the same. And maybe you can kind of relate to this particular case of, you know, say you have some object which is kind of a little bit sticky or something like that, right? And you're trying to slide it, and then you're pushing on it, and then you go, oh wow, it's stickier than I thought, and then you push it, and it finally starts moving. But then when it starts moving, you're going, oh my god, it's going like a little bit too fast, and so I got to like ease back off it, right? And then so you do this kind of little compensation move where you give it a bit of a harder push at the beginning, and then you sort of ease back on it, and then once it's moving, you know it's moving, and so you know you can kind of relax a little bit. Like if you're moving a very heavy object, sometimes this is what you do. You give it a little bit of a push at the beginning just to get it going, and then you can sort of ease back and then just push with a constant force. Have you guys experienced that? Yes. Yeah. So basically, this is exactly this effect that actually usually the kinetic friction, this Fk, is actually this Fs is actually the largest value that the static friction can possibly provide, right? So this Fs is actually a little bit bigger than Fk usually. Okay, and again, Fk is given by a formula that looks just almost like the static friction one, except that this coefficient here is a different coefficient. It's the coefficient of kinetic friction, and the fact that the kinetic friction is a bit less than the static friction, what I was just saying there, how that manifests itself is that basically this mu k is usually a bit smaller than the mu s. Right? Okay, so that was the case when I was pushing it and then it's going at constant velocity. Now let's look at the case when, like this was the first example when, say this is just like when just gives it a push at the beginning and then doesn't push it all the way, it slides to a stop, right? So in this case, so that would be that so Bob is no longer pushing it. The act of the first force was just to sort of give it some initial velocity. Afterwards, basically Bob is no longer pushing it. So now this thing's moving with some velocity, but it's going to grind to a halt at some point here. And then the only force that's acting on it is the friction force. So in this case, there's only one force acting on it, so that's F, and it's going to act in the opposite direction to the movement. So the velocity is this way, the force will be the other way. So in that case, the object will slow down, or if Bob is actually, he keeps on, say Bob is a little bit of a nutcase, like he's going to push it and then he's going to keep on pushing it until it just keeps on accelerating and gets faster and faster. This is not how you normally push things because it's a bit uncontrolled, but if he pushes it, then if he keeps on applying force, and if this force doesn't balance it, then of course this thing will keep on speeding up because you're constantly applying force. And basically, in all these cases, the Fk is the same, and the main difference between this kinetic friction and the static friction is that this is actually just always just a constant force, right? So once you're moving, it doesn't really matter if the object is moving faster or slower or anything like that. At least the level of this formula, the force is just a constant. So in all these three situations, you just take the force to be given by this relation. And this is quite different to the static friction case because the static friction was some dynamical thing that always matches whatever you're doing. So if you're providing 10, it'll provide 10 back. If you're providing 5, it'll provide 5 back. But then for the kinetic friction case, once it's moving, it's just providing a constant force and it's not changing particularly with whatever force you're applying. So you could be pushing with a bigger and bigger force, but this one would be just providing force that is pushing back on you. This is a bit like what I was talking about with when you're trying to get something going, give it a bit of a harder push to get it going, and then finally it will start sliding you can ease back off it, and then you can go to a kind of a more steady velocity. So this would be the force that you're applying with time. So you're applying a larger and larger force to trying to get the thing to move. Finally, it moves, and then immediately you feel like that it's moving, so you ease back on it, right? And then here you might sort of overcompensate and then ease back too much, and then push forward a bit, So you have a kind of a feedback process between you and the object. So you're sensing how fast it's going, and then you're adjusting just the right amount of force so that it's moving at a nice constant velocity. And so this is the force that you eventually arrive at. Okay. Yeah, I think I explained everything already. Alright, so let's maybe just do this question. So a block lies on the floor. What is the magnitude of the frictional force on it from the floor? Right. Okay, so A is just that. So you don't need any information actually. So here's a block, it's on the floor. So what's the frictional force on it? Sorry? 0. Right, 0, yes. 0 because not even moving. So the only forces on it are gravity, normal force. It's not moving. There's nobody pushing on it, so there's no force. Okay. Horizontal force, 5 newtons applied to the block. The block does not move. What is the magnitude of the frictional force? 5, yes. Because just like the TV, you push for 5, it will push back to 5. If the maximum value of the static frictional force on the block is 10 units, will the block move if the magnitude of the horizontally applied force is 8? No. Yeah, no. Because the maximum... Yeah. This is still in the range where it can provide the force it's a matching force. So you can provide a maximum up to 10, so if I'm providing 8, you can still push back with 8. What about if it's 12? Yes, that's right. So it will start moving. What is the magnitude of the frictional force in part C? Right. I think I already said the answer. It's 8. Okay. All right. Maybe we can leave that stuff there because this is sort of a new topic. So let me get the Zoom set up now. Might take a few minutes.